All right, welcome back to Organic Chemistry. This is the second in a four-part presentation on nuclear magnetic resonance. If you did not watch the first presentation, I would suggest you go back and do so. In the first presentation, we introduced sort of the background of NMR, and we talked specifically about carbon-13 NMR and what we can learn from a carbon-13 NMR spectrum, and a little bit about how that works. Let's just recap. There's really three things that you look for in a carbon-13 spectrum. The first thing that we found was that every unique carbon gives a unique signal. Now, this is because the signal in the carbon-13 spectrum is somehow related to, it is related to the energy of the excitation-relaxation transition. And that energy is affected by what's called the local field. That is the effect of the electrons around that nucleus. Any carbon that has a different arrangement of electrons will have a different energy for that transition. And therefore, you will see you will see different lines. The difference in arrangement of electrons could be something like hybridization, but it could also be what atoms are attached nearby. And in fact, even if atoms are several positions away, they will still exert an influence, at least enough to see different signals. So, for instance, a carbon that is 4 positions away from a chlorine will have a slightly different energy for the excitation-relaxation process than one that is 5 positions away from a chlorine. Now, because of this, different carbons will give different signals. And so if there's no symmetry in your molecule, there will be the same number of signals in the spectrum as the number of carbons in the formula. On the other hand, if there is symmetry, like for instance take ethane. In ethane, it's completely symmetric. The 2 carbons are identical to each other. If you turn the ethane around, you couldn't tell the difference. So therefore, those 2 carbons, since they have exactly the same arrangement of bonds, have exactly the same energy for that transition, and therefore they only give one signal for ethane. So if you have symmetry, you will see fewer signals in the spectrum than carbons in the formula. The second thing we addressed in our previous presentation was what that x-axis tells you a little more specifically. Not just that those carbons are different from each other in terms of the bonding environment around the nucleus, but it also tells you about the bonding environment. sp3 hybridized carbons come in one general area of the spectrum, and sp2 come in another general area of the spectrum. Also, electronegative elements nearby will lead to a shift within those general areas. So, for instance, sp3 hybridized carbons will give you signals somewhere between 0 and 70, plus or minus, depending. But just a pure alkane, just CH, CH, CC, CC type bonds, will have those signals more to the right within that 0 to 70 region. But when there are strongly electronegative elements nearby, the signal will be shifted to the left. So a CO bond, which is a carbon connected to the second most electronegative element, will come very far to the left, like within that region, so like around 65. On the other hand, a carbon attached to a nitrogen will give a signal that's not shifted quite as far. Other elements as well. Within the sp2 hybridized carbon region, sp2 hybridized carbons come, say, 100 to 200. But a carbon-carbon double bond versus a carbon-oxygen double bond will come at different regions. Carbon-carbon double bonds come more like 100 to 150, but a carbon-oxygen double bond can go as high as, can actually go as high as like 210 or 220, but are more like closer to 200. And then finally, in some instances, you will have other experiments. Now, decoupled carbon-13 NMR, which is the first type of thing we've been discussing only gives a single signal per carbon. But, or, leaving aside the whole question about symmetry. But there are other variations on carbon-13 NMR that will give patterns, called splitting patterns, that tell us about the number of hydrogens attached to each carbon. All right, how can we put this together? There is no one right way to solve a carbon NMR spectra or spectral problems in general. And when I say solve a spectrum, what I really mean is start with a spectrum or a series of spectra and maybe some other information like the chemical formula or maybe some chemical information, and then figure out what the structure is. That's what I mean by solving a problem. There's no one right way. This is my way. So you can do it whatever way you want, but I think this is a systematic way that will do you well. First thing, whenever I start by looking at the formula, assuming it's provided, and for us it will be provided. Certainly for now. Maybe I'll show you some examples without a formula, but those would need some other information as well to try and get that formula. But when I start with the formula, I can calculate the number of degrees of unsaturation. We discussed that in a previous presentation, the one called spectroscopy background, or maybe I called it light. I think I called it light. Anyway, by looking at the chemical formula, I can figure out how many rings and or pi bonds there are. One thing to keep in mind is if there's a very large number of degrees of unsaturation, that is often that would be consistent with a benzene ring or something like a benzene ring. Doesn't prove it, but when I have 4 or more degrees of unsaturation, I think to myself that there is quite likely an aromatic ring, or a benzene ring, sorry. Benzene is an aromatic compound. We will learn more about those in a subsequent chapter. Then, if I have an IR, I will look for key functional groups. And as when we discussed IR, I mentioned, I spend very little time on IR. I look for the presence or absence of OHs and NHs. I look around 33 to 3400. I look around 3000, and to the right of that I see sp3CHs, and to the left I see sp2CHs. Around 2200 I see CC and CN triple bonds, and around 1700 I see a CO double bond. So when I look at an IR spectrum, I am just simply looking for either the presence or absence of those functional groups. And then I come to the carbon-13 NMR, and I go through it in order. First thing I do is I count the signals. I just simply say, oh, there's 6 carbons in the formula, there's 6 lines in the spectrum, I have no symmetry. Or there's 6 carbons in the formula, but there's only 4 lines in the spectrum, so there must be some sort of symmetry. Secondly, I look at the chemical shift. I look where those come. I note, oftentimes I'll write this directly on the spectrum, or I'll write it down in my notes to the side of the spectrum, which ones represent sp3 hybridized carbons, which ones represent sp2 or even sp hybridized carbons. I note which ones are carbons close to strongly electronegative elements. And then finally, if it's available, I will go through each of the signals and see what splitting information tells me. That is, I'll note, again, I'll often write it directly on the spectrum or to the side in a set of notes. I'll say the signal at 40 represents a CH3, and the one at 50 represents a CH2, and the one at 100 has no hydrogens, or whatever. Then, if I had it, I would go on to the proton NMR. We haven't even covered hydrogen NMR, so I'll ignore that for now. Then, I take a look at all the notes I've come up with, and I draw out the pieces. I should be able to figure out, based on the formula and based on the information from the spectra, I should be able to figure out what sorts of things are involved in that molecule. That is, I've got a CH3. And I'll write down a CH3. I've got a CH2 that's next to oxygen, so I'll write down a carbon with 2 hydrogens and an oxygen attached, etc. No matter, what I've got. And sometimes I might realize that because of symmetry, I might need more than one of those things, right? Remember we said that when there's symmetry, one signal will represent more than one carbon. So maybe I'll realize that I need one more carbon and 3 more hydrogens, but there's symmetry, and so I'll realize that instead of having one CH3 group, I have 2 CH3s that are related by symmetry, in which case I'd write down 2 CH3 groups. In my next step, I call the next step the Tinker-Toy step. In the Tinker-Toy step, I stop thinking about chemistry, and I remind myself of my childhood when I had, whatever you had as a kid. Blocks, Tinker Toys, Lego, Connects, whatever. You had you probably, I'm sure, at some point, you played with some construction toy. And when you're playing with a construction toy, you're not thinking about chemistry, you're just thinking about which pieces connect to which pieces and how many things you can connect together. I know, for instance, that carbon makes 4 bonds, that hydrogen makes 1, that oxygen makes 2, nitrogen 3, etc. And so if I have a CH3, I've got sort of an empty spot where I've got one more connection I can make. If I have a CH2, I can connect 2 things to that. If I have a CH, well, I need to account for 3 more connections. Or a C with no hydrogens, I would have to account for 4 more connections, etc. If I have an OH, well, oxygen makes 2 bonds, so I've got to make 1 more connection, whatever. Now I've got these pieces, and I know how many things they connect to. And in the Tinker-Toy step, I just think of them as pieces that I connect to each other. They might connect to each other in more than one way. So I might come up with 2 or 3 or maybe more possible combinations of the pieces in the molecule. Well, then I'm going to go back and check my work. I'm going to go look at the spectra and decide which one fits best. Even if I only came up with one possible structure, I'm still going to check my work and make sure it fits. Now, a couple of other notes in doing this. Notice I'm being very systematic with this. I find the people that get very confused by spectroscopy are the ones who are just sitting there with an IR and a carbon NMR and a hydrogen NMR or whatever information they're provided. And they're just sort of staring back and forth, and they don't know where to start. I think if you kind of work through, you look at each spectrum in turn and write down, that's my next point, write things down. Don't just try and keep it all in your head, but actually write down, oh, this signal is a CH3. This signal in the IR tells me that I've got an OH, or whatever. Be cognizant both of what's there and what's not there. I might know from my IR that I do not have an OH, and that might help me put together the pieces. And finally, interpret the unclear in light of the clear. That is, start with the stuff that's obvious. Start with the stuff that's totally unambiguous, and then see how the more equivocal data fits into the picture shown by the very clear data, rather than trying to start with the confusing signals and then sort of come up with a proposal and then try and fit everything into that proposal, whether or not it truly fits. Always start with the things that are obvious and then come to the more equivocal things. All right. Oh, this is just my picture of Tinker Toys. If you didn't play with Tinker Toys, that's them on top. Legos, Erector Set, Connects, imagine whatever toy you played with. When we're in the Tinker Toy step, we simply think of our molecule as a combination of pieces. And in our combination of pieces, for instance, on these Legos, this one has, 8 bumps on the top, and this one has 4, and they're going to, I couldn't turn this one upside down and put it on top of this because I got to put the, the studs into the holes on the bottom, for instance. So we just think of how things can connect together and how many pieces I can connect to a given piece. Like these Tinker Toys have like 8 connection points. Well, I guess they have 9 if you consider the center axle. The sticks in Tinker Toys can essentially attach 2 things because one on either end, for instance. Okay, let's put this into play. Here's an unknown with the formula C3H5Cl3. This is a carbon-13 NMR. I know it's a carbon NMR because the scale is 0 to 200. Once we get to hydrogen NMR, we'll see that the scale in hydrogen NMR is 0 to 10, and it's very obvious that you're dealing with proton versus carbon. I also have here in parentheses splitting information. So in this example, rather than showing you an off-resonance decoupled carbon-13 spectrum, I am just indicating to you that in the off-resonance decoupled carbon-13 spectrum, this signal is replaced by a quartet, this one by a doublet, and this one by a doublet. So what you'll see for these little abbreviations is S for singlet, D for doublet, T for triplet, Q for quartet, and not so much here, but in hydrogen NMR we might refer to multiplets, things that are basically more complex looking. All right. These are what I have. I'm going to have to figure out what my molecule is based on this information. So I am going to start out not with the spectrum, but with the formula. And when I look at the formula, I figure out that this molecule has 0 degrees of unsaturation. To remind you of how we calculated degrees of unsaturation was equal to the quantity of 2 plus twice the number of carbons, plus 1 times the number of nitrogens, plus 0 times the number of oxygens, minus 1 times the number of hydrogens, minus 1 times the number of chlorines, all divided by, halogens, all divided by 2. So in this case, we've got 2 plus 6 minus 5 minus 3. Well, that all adds up to 0. Divided by 2 is still 0. This molecule, whatever it is, has no rings and it has no pi bonds. Okay. You could actually probably just stop there and draw a different isomers of C3H5Cl3 because there's actually, it turns out, not that many isomers. But let's do this in a systematic fashion. I then look at the carbon-13 spectrum. And how many lines do I have in the spectrum? 3. What's that tell me? I don't have any symmetry, because each of my 3 carbons in the molecule is in a unique bonding situation. And that's why these 3 lines show up at different places along this x-axis. So I see that there's no symmetry. Oh, I should have noted I don't have an IR, and so I can't get information from the IR. Okay. But now I'm going to look at where those carbons come in along that x-axis and see what that tells me. Remember, signals roughly, I said about 0 to 70. This one over here is like at 77 or something like that. That doesn't, I mean, those are rough borders. So these are all really within the sp3 region. It can't be in the sp2 region, which is 100 to 200. It can't be in the sp, which is right in here. Plus, I should say, we know that there's no double bonds. So these are sp3 hybridized carbons. But not just sp3 hybridized carbons. Within this region, notice this one is more to the right, and these 2 are more to the left. What did we say about those regions? We said electronegative elements will cause things to shift to the left within those regions. If I look at my formula, I notice I've got chlorine, which is more electronegative than carbon and hydrogen, right? It's the 4th most electronegative element on the periodic table. And that's going to suggest to me that these 2 guys over here are near the chlorine. On the other hand, this signal represents a carbon that is not directly attached to chlorine. All right, what else do I see in the spectrum? I see information from the splitting in the off-resonance decoupled. This one here is a Q. Q is a quartet. What does a quartet in the ORD tell us? Oh, CH3s give us a quartet. And so I know that this signal is a CH3. On the other hand, this one's a doublet, and this one's a doublet. What sorts of things give me doublets? Well, those are CHs. It's the n+1 rule. If I'm attached to 0 hydrogens in the ORD, I will have a 0 + 1 or a 1 peak pattern, a singlet. If I'm attached to 1 hydrogen in the ORD, I will have a 1 + 1 or 2 peak pattern, a doublet. If I'm attached to 2 hydrogens, I will have a 2 + 1 or a 3 peak pattern, a triplet. And if I'm attached to 3, I will have a 4 peak pattern, which is a quartet. All right. So if I look at this, I know that I've got a CH3, a CH, and a CH. And that actually accounts for all the carbons and all the hydrogens. So let's draw those pieces out. But that's not all my pieces. I'm still missing the chlorine, so let's take those out. So let's start putting things together. I could just start from here, and that would be a pretty easily way to do it, because there's not that many. There's, in fact, well, there's only one way to put the pieces together, because some pieces, you'll notice, make one connection. This piece makes one connection, this piece makes one connection, this piece makes one connection, and this piece makes one connection. On the other hand, these two pieces make three connections, because if I've got a CH, carbon makes 4 bonds, I've got to account for 3 more connections. If I've got a chain of people holding hands, how many hands are the people in the middle holding? 2. How many hands are the people on the end holding? Well, the guy at the end of the chain is only holding one hand. Same thing here. If this only makes one connection, it has to be somewhere on the outside. Same thing with these. But these two have to be somewhere in the middle, because they make 3 connections, and so you got to connect this other stuff up to these. I can't connect this chlorine to that, because then I just have chloromethane, which should be a separate molecule. So these chlorines are going to have to be attached to these. But you know what? We knew that anyway, right? We knew that the CHs were near chlorine, and this guy wasn't. And so let's connect, the chlorines to these. If I attached all 3 to one, well, that would be chloroform. That would be a separate molecule. If I attach 3 to the other, so I'm going to have to attach 1 to this and 2 to this, or 2 to this and 1 to that, but it doesn't really make a difference. It turns out there's only one way to put these pieces together. I've got my CH3 piece, I've got a C with one H and a C with one H, and the chlorines are attached to those carbons. Now we should always go back and check ourselves. We should make sure this fits the data. How many degrees of unsaturation does this molecule have? It doesn't have any. No rings, no pi bonds. Is there symmetry in this molecule? No. This is 1,1,2 trichloropropane. And if I asked you which is position 1, you would unambiguously point to this one. This one is unambiguously position 2, and this one is unambiguously position 3, because there is no symmetry. Do I have sp3 hybridized carbons? Yes. Is one of them a CH3 and the other 2 CHs? Yes. Are the CHs near the chlorines? Yes. This seems to fit everything we know. In fact, we could even go a little bit further and remember I said that being sp3 is generally like 0 to 70. This one's a little further to the left than 70, but notice one of my carbons is close to 2 chlorines and the other one is close to 1. You might expect that being close to 2 chlorines, if one chlorine shifts things a little, 2 chlorines will shift things more. And so we could even figure out that this signal represents the carbon with 2 chlorines, and this signal represents the one with 1 chlorine. We weren't asked to do that in this question. We just wanted to come up with the fact that this was 1,1,2 trichloropropane. All right, let's do another. C3H6O. I'm going to start out by looking at the formula before I even look at the carbon-13 spectrum. And I am going to realize that this molecule, C3H6O, well, you tell me, how many degrees of unsaturation does it have? We know that the degree of unsaturation is going to equal 2 plus twice the number of carbons plus 1 times the number of nitrogens plus 0 times the number of oxygens minus the number of halogens minus the number of hydrogens, all divided by 2. So this is going to equal 2 plus 6 plus 0 for the oxygen minus 6. So 2 plus 6 minus 6 is 2. Divided by 2 is 1. So I have 1 degree of unsaturation. That means I've got 1 ring or I've got 1 pi bond. I don't know yet which. If I have a pi bond, I don't know if it's a carbon-carbon pi bond or if it's a carbon-oxygen pi bond. We'll figure that out by looking at the spectrum. Because when I look at the spectrum, well, first thing I'm going to do is I'm going to ask myself, is there symmetry? No, there is not. Because there are 3 carbons in the formula, and there are 1, 2, 3 signals in the spectrum. So this molecule has no symmetry. Okay, what do I know about the chemical shift? Signals in this region are sp3, and signals in this region are sp2. Seems like we'll probably have a double bond, right? Double bonds involve sp2 hybridized carbons. And in fact, we've got two sp2 hybridized carbons, so it seems like we've got a carbon-carbon double bond. What do we see over here? sp3 hybridized carbons come 0 to 70, give or take. But this signal, it's not over here by like 10 or so. It's over here closer to 70. What sorts of things come over there? Things that are shifted due to the presence of electronegative elements. So it appears that this carbon is for an sp3 hybridized carbon that is close to an oxygen. Okay. These are for two sp2 hybridized carbons, most consistent with a carbon-carbon double bond. What else do we see? We have information from the off-resonance decoupled carbon-13 spectrum. That is, we know that in the ORD, the signal around 138 or so is a doublet. CHs give doublets. We know that the carbon that gives a signal somewhere around 115 is a triplet. CH2s give triplets. And we know that the carbon that gives a signal around 62-ish is a triplet. That's a CH2. All right, that's it. I have gone through my spectrum and the formula, and I have written down all of the information that I see. I have to put this together. I'm going to draw out my pieces. I know that I've got a CH, a CH2, and a CH. Okay. Sorry, I had to pause the recording there. We saw that we had sp2 hybridized carbons that were respectively a CH and a CH2. And we saw an sp3 hybridized carbon that was a CH2. So I've got those here. But are those all my pieces? 1, 2, 3 carbons. 1, 2, 3, 4, 5 hydrogens. 6 hydrogens. There must be one more hydrogen. Oh, and there's also got to be an oxygen. Now, I know more information than this, but let's just stick with this for the moment. I mean, let's see how we can put these things together. Now, the first thing I notice is that these are sp2 hybridized. They're involved in double bonds. A double bond involves two sp2 hybridized atoms. Now, in this case, they must be double bonded to each other. Now, there is such a thing as a CO double bond, but that would come more like around 200. Plus, I need both of these carbons to be involved in double bonding. And so the only real explanation is that they're double bonded to each other. But I've got a carbon-carbon double bond piece, but I've also got a CH2, an O, and an H. Notice if I connect these up together, I'm going to get a carbon-carbon double bond with one more place to attach something. That's got to go at the end of a chain. This H has to go at the end of a chain because it only makes one connection. Whereas this and this make two connections, and so therefore they go in the middle of a chain. Turns out there's two ways to put those pieces together. I've got my carbon-carbon double bond part. I've got my H. Those are kind of the bookends. And in between, I've got the CH2 and the O, or the O and the CH2. That's it. These are the only ways that I can put these pieces together and have valid Lewis structures with the right number of bonds per atom. Notice I should note that I'm not drawing in the lone pairs and stuff. I'm just trying to get the structure. But we all know that that oxygen has two lone pairs, for instance. Now I'm going to go back and check my work, and hopefully one fits the data and the other does not. All right, so what do I know? Do I have 1 degree of unsaturation? Yeah, that one has 1 degree of unsaturation, so does that. Do I have no symmetry? Well, this one doesn't have any symmetry, so that fits that. Same here. This one also doesn't seem to fit that. Do I have 2 sp2 hybridized carbons and 1 sp3 hybridized carbon? Yeah, that's true of both. The sp3 hybridized is definitely by oxygen in both. We might make some conclusions about this carbon, but that's a little bit unclear. A CC double bond with an oxygen next door, this one's shifted. It's not shifted all the way over here, but maybe I'm not going to put stake on that. I'm not going to use that to solve my problem. But here, this next piece of information will help us nail it down. A CH, a CH2, and a CH2. This one has a CH2, a CH, and a CH2. That other hydrogen isn't attached to any of the carbons. This one has a CH2 here, a CH here, and how many hydrogens here? Oh, 3. That doesn't work. And so I know that it can't be that. If I had other information, like if I had an IR, that would also be very helpful. Because, for instance, in the IR, I would see a very strong signal for the OH. I don't, in this case, have an IR, but I don't need one, because I've put together the pieces in the only possible ways that they could go, and by process of elimination, I've decided that this must be prop2ene1-all, or propenol. And that's my only possibility. That's solving carbon-13 spectra. There are a lot of practice problems in the course material. There are practice problems in your textbook. You could just Google carbon-13 NMR practice problems, and I'm sure you could find a lot more. I've got sample exams, I've got handouts, etc. I highly suggest you do more practice on solving carbon-13 spectra. But in my next presentation, we're going to add another piece to the puzzle. We're going to look at proton NMR spectra and find out that that is also a very powerful technique to solve structures. And then we'll find that we could either solve structures with proton spectra alone, or we could combine proton, carbon, and even IR together, and other things as well, in a very powerful way to solve the structure of organic molecules. All right, come back in part 3 of this presentation, and you will learn about proton, also known as 1H NMR.